Before life existed on Earth, there was just chemistry, this sort of soup of molecules. No plan, no designer, no blueprint. The central question of origin life research: how do useful molecules emerge from that chaos? The Williams Lab at Georgia Tech has a clear framework: chemical evolution. Water acts as a selective filter, helping molecules interact, relentlessly destroying them through hydrolysis. Molecules that resisted long enough survived and eventually became life, not by design, by selection. This hackathon we want to test out if this principle holds up computationally. Most original life models require you to specify the chemistry first. What molecules, what reactions, and what pathways. But prebiotic reaction space is fundamentally unknown. What about entirely alien environments like Europa and Enceladus? That's why we built Chemtrain to answer. Without encoding specific chemistry, can water selection alone drive systematic molecular complexity? And Chemtrain is a digital twin of prebiotic aqueous chemistry, implemented entirely in Python. Footage is captured live from Chemtrain. So periodic building blocks collide and then bond across a 2D grid growing into chains. Then these chains can lock into hydrogen bonded assemblies. These assemblies can then form catalysts. Then we reduce building block chemistry into coercing properties: hydrolytic resistance, hydrogen bonding donor acceptor, and bonding formation properties that are all sampled from broad distributions representing true abiotic diversity. At every time step, water attacks these bonds, and hydrogen bonded assemblies protect their bonds, and catalytic behavior emerges only when the right building blocks confirm. These rules produce completely emergent behavior with hydrogen building blocks, as you see. And running property simulations with realistic population level trends, you can see that there's skewing towards hydrolytic resistance, as well as overall assembly growth, driven by water selection alone. And Chemtrain is intentionally minimal, 2D few properties to isolate a single variable, water. This minimal rules isn't a limitation. Chemtrains are built to easily scale, so that we can add features like wet dry cycling, affected hydrolysis rates, solubility, or kinetics, progressively enriching our simulation. And by adjusting parameter distributions, we can model ion-rich oceans, vents, or tidal pools, environments with completely different chemistry, but same pressure. This scalability transfers Chemtrain from proof of concept into a platform for modeling any prebiotic environment.